In today's video, I will introduce, explain, and illustrate the quotient rule, which enables us to differentiate a quotient of expressions in terms of the derivatives of the numerator and denominator. I will apply the rule to differentiate some algebraic and trigonometric functions. And I will also apply it to sketch a curve that is referred to as the Witch of Maria Agnesi. Let us begin with the statement of the quotient rule. Consider function y of x, which is a quotient u divided by v, where u and v are themselves functions of x. The quotient rule states that the derivative of y with respect to x is v times the derivative of u minus u times the derivative of v all over v squared. And we can express this using Leibniz notation, the way you see it here. Equivalently, using function notation and a dash to denote the derivative, the quotient rule says y dash is v u dash minus u v dash all over v squared. It might look complicated at first, but it's remarkably elegant considering the task at hand, which is to differentiate a possibly highly sophisticated function expressed as a quotient. That we can do it at all is surely something of a miracle. The quotient rule, in fact, follows from the product and the chain rules. The reason is worth investigating, as it consolidates your understanding of these rules and the way they fit together and makes your technique more robust and stronger. Put y equal to u over v, which we can write as a product u times 1 over v, which we can further rewrite as u times v to the minus 1. Because this expression is a product, naturally we can apply the product rule. So that dy dx equals the first factor, u times the derivative of the second factor, plus the second factor, v, to the minus 1 times the derivative of the first factor. But the derivative of v to the minus 1 with respect to x may be expanded to become d dv of v to the minus 1 times dv dx by the chain rule, which becomes minus 1 times v to the minus 2 times dv dx, which simplifies to minus dv dx over v squared. Hence, dy dx becomes u times this expression plus the second piece, which can be rewritten as du dx over v. And the first and the second pieces can be rewritten so that the whole thing can become v du dx minus u dv dx all over v squared, which is exactly the form of the derivative in the quotient rule. Let us consider some examples. 。 . 。 . 。. 。. 。. 。. 。. 。. 。. 。. 。. 。. 。. 。. 。. 。. 。. 。 . 。 . 。 . 。 . 。 . 。 . . . 。 . . 。 . . . . . . . . .
。 .
Let y equal the quotient x squared plus 1 divided by x. And our task is to find the derivative y dash. We can solve this directly by splitting y up into two fractions, which becomes x plus x to the minus 1, and then differentiate each piece. The derivative of the first piece is 1, and the derivative of the second piece is minus 1 times x to the minus 2, which becomes 1 minus 1 over x squared, which we can leave as that or rewrite as a single fraction, x squared minus 1 over x squared. An alternative solution is to apply the quotient rule, because y is the quotient of u divided by v, where u is the numerator, x squared plus 1, and v is the denominator, x. So that u dash is 2x and v dash is 1. So by the quotient rule, we can have y dash is v u dash minus u v dash all over v squared. And we can put all the pieces together, expand and simplify using a couple of steps to get x squared minus 1 over x squared, which agrees with our first direct solution. Here's a more complicated expression for y. And our task is, again, to find the derivative y dash. Observe that y is the quotient u divided by v, where u is the numerator and v is the denominator, with derivatives u dash and v dash respectively. We apply the quotient rule and put all the pieces together. The derivative of y dash is complicated, and I'm not even going to try to simplify it further. I just made up this example for the purpose of illustration and have no idea what the graph of the function looks like, or even whether the function corresponds to some interesting or important problem. The point I want to emphasize in an example like this is that we can find the derivative quickly by means of the rules that we develop. And the process becomes quite mechanical and procedural. Indeed, something remarkable has happened. Just in the space of a few videos, we have moved from the basic definitions of the derivative to being able to differentiate very sophisticated functions fluently and easily. Even though we don't know what the curve looks like, this expression for the derivative, in principle, allows us to find slopes of tangent lines at any given point in which the expression is defined. In my opinion, this is an extraordinary achievement. And if you follow the development up to this point, then you should be congratulated on coming so far so quickly. In an earlier video, I told you what the derivative of tan x turns out to be. Let's see if we can discover it for ourselves. Observe that tan x is sine x over cos x, which becomes a fraction u over v, where u equals sine x and v equals cos x. so that u dash is cos x and v dash is minus sine x. By the quotient rule, the derivative of tan x with respect to x becomes v u dash minus u v dash all over v squared. And we can put the pieces together. The denominator becomes cos squared x, whilst the numerator becomes cos squared x plus sine squared x, which by a certain identity simplifies to 1 by the circular identity. And the answer becomes 1 over cos squared x. This agrees with the answer that I told you some time ago without giving any reason. Now, there is some common notation and terminology that you should become aware of involving trig function. And those terminology has to do with what we call the secant. We put sec x equal to 1 over cos x, the reciprocal of cos x, where sec is an abbreviation for secant. This word is related to lines, drawing certain points in diagrams involving the unit circle in the context of more advanced trigonometry. But I won't go into the details. You can always look it up for yourselves. This new terminology, the derivative of tan x, becomes a square of sec x, which is written as sec squared x. You can continue to think of the derivative as 1 over cos squared x if you like, but you'll almost certainly see the sec notation in your mathematical travels. The secant function simply reciprocates the value of the cosine function. There's special terminology also for the reciprocating value of the sine function. CSC x equals to cosec x equal to 1 over sine x, where CSC and COSEC are both common abbreviations for cosecant. There's one more. Put cot or COTX equal to cotan x equal cos x divided by sine x, which is the reciprocal of tan x. And here, cot and cotan are common abbreviations for cotangent. Thus, cosecant and cotangent again have geometrical interpretations in more advanced trigonometry, which I again wouldn't go into again here. And we will not need either of them in this course. We have from before the derivative tan x is 1 over cos squared x, expressed also as sec squared x. And we can easily check that the derivative of cot x or cotan x is negative 1 over sine squared x, which you can express as minus cosec squared x. So far, I've introduced and illustrated the quotient rule, which enables you to differentiate a quotient of expressions in terms of the derivatives of the numerator and denominator. I also explain how it comes about as a result of applying the product and chain rules. by expressing the quotient as a product, the numerator with the reciprocal of the denominator. I also gave some contrasting examples, and importantly, found a formula for the derivative of tan x, namely the reciprocal of cos squared x, which can also be expressed as sec squared x, where sec is an abbreviation for secant. The values of the secant function are the reciprocals of the values of the cosine function. In this part of the video, I will apply the quotient rule to explore the behavior of the curve y equals 1 over x squared plus 1, known as the witch of Maria Agnesi. Our main example is a curve of fundamental importance in the theory of rational functions. That is, a ratio of polynomials, and involves reciprocating the quadratic x squared plus 1, which has a special place in mathematics, being the simplest polynomial you can think of that does not have any roots over the real number system, since it's always greater than or equal to 1 for any real number x. So it cannot possibly be 0. In fact, this innocent and unassuming quadratic leads to the construction of the arithmetic of complex numbers C, with quite remarkable properties, which I hope you will learn about in more advanced courses in mathematics that follow on from this course. Consider a function with the rule y equals 1 over x squared plus 1. Its domain is all the real number line, since x squared plus 1 is always non-zero. One can ask what its graph looks like. The resulting curve is known as the witch of Maria Agnesi, named after an Italian mathematician, Maria Agnesi, who lived and worked in the 18th century and wrote one of the first treatises on calculus. The word witch, in fact, comes about by a linguistic accident in translating texts from Latin, though happily the name of the curve survives and is evocative of a witch's hat, as you'll see in just a moment. Let's work through our usual checklist for sketching a curve. In this case, for y equals 1 over x squared plus 1, the y-intercept is the value of y when x equals 0, which is 1. There are no x-intercepts, as the reciprocal of x squared plus 1 is always positive. For asymptotic behavior, it's clear that the limit of 1 over x squared plus 1 is 0 when x gets large. When x gets large and positive, or large and negative, so that the x-axis becomes a horizontal asymptote. We then investigate the derivative, which gives us information about when the curve is increasing or decreasing, and for finding any turning points. To set up the chain rule, we write y as x squared plus 1 to the minus 1, which becomes u to the minus 1, where u equals x squared plus 1. So the derivative y dash, which is dy dx, becomes dy du times du dx by the chain rule. which is negative u to the minus 2 times 2x, which we can rewrite as negative 2x over u squared, and then express everything in terms of x to get y dash equals negative 2x divided by x squared plus 1 squared. Notice that the denominator is always positive, and y dash equals 0 precisely when the numerator is 0. That is, when x equals 0. We can now easily build the Sine diagram. We have y dash equals 0 when x equals 0, and either side of 0 has the opposite sign of x because the denominator is positive. So the sign is determined by the numerator, giving the pattern positive, negative, corresponding to increasing, decreasing, with a global maximum occurring when x equals 0. We can put all of this information together, locating the y-intercept, the fact that the x-axis is an asymptote, and the turning point of x equals 0. The qualitative behavior parallels what we saw when we analyzed the Gaussian curve, y equals e to the minus x squared, in an earlier video. One expects to be able to join the pieces together to create a smooth curve that also looks bell-shaped. There appear to be 2 points of inflection where concavity changes. To be sure about the behavior with regards to concavity and to locate the inflections, we need to investigate the second derivative, y double dash. Because the first derivative, y dash, is a rational function, we should expect to apply the quotient rule. To investigate the second derivative, we write y dash as u over v, where u is the numerator 2x, and v is the denominator x squared plus 1 all squared. So u dash is minus 2, and v dash is dv dx in Leibniz notation, which is dv dw times dw dx by the chain rule. If we make this substitution, w equals x squared plus 1, which becomes 2w times 2x, which is 4 times x squared plus 1. We now have all the ingredients for the quotient rule, and inserting all the pieces gives this complicated looking expression, which simplifies after some effort to the rational function 2 times 3x squared minus 1 divided by x squared plus 1 cubed. And you can check yourself to see that this is so. It's a good exercise in algebraic manipulation. Note that the denominator ends up being the third power of x squared plus 1. because of cancellation with a copy of x squared plus 1 in numerator. Thus, we end up with this very nice expression for y double dash. Note that the denominator is always positive, being the cube of x squared plus 1, which is positive. Also, y double dash is 0 precisely when the numerator is 0, which occurs when x is plus or minus 1 over the square root of 3. We can now build the Sine diagram with y double dash being 0 for x equal to plus or minus root 3. The pattern of positive, negative, positive, determined by the sine of 3x squared minus 1, corresponding to concave up, concave down, concave up, with inflections occurring when x equals plus or minus 1 over root 3. We can add this extra information to the previous compilation when we work through the curve sketching checklist. This completes the sketch of the curve y equals 1 over x squared plus 1, affectionately known as the witch of Maria Agnesi. The curve is also in the shape of a bell, though it certainly is not the same as a Gaussian curve. However, they do share some similarities. I would like to finish by establishing a remarkable connection between the witch of Maria Agnesi and trigonometry. Recall the single branch of the tan curve that results by restricting the domain to the interval between plus or minus pi over 2, sandwiched between two vertical asymptotes, and satisfies the horizontal line test, certified as suitable for inversion, with inverse function obtained by reflecting in the line y equals x to get the inverse tan function, which is increasing and sandwiched in between two horizontal asymptotes. We can see how the slopes of miniature tangent lines behave as we move from left to right along the inverse tan curve. Notice how the slopes are all positive, and the steepest slope appears to be at the origin and takes the value 1. And the shallowest slopes appears to the far left and far right and appear to be approaching 0. The slopes of tangent lines are just the derivatives, and this behavior suggests that the derivative of the inverse tangent function behaves qualitatively like the function that gives rise to the witch of Maria Agnesi. Maybe if y equals inverse tan of x, then y dash equals 1 over x squared plus 1. It turns out to be true. The proof emerges from the magic of Leibniz notation. Watch. Start with a circular identity. sine squared x plus cos squared x equals 1. Divide through by cos squared x eventually to get tan x somehow into the game. This becomes sine x over cos x all squared plus 1 equals 1 over cos squared x, which can be rewritten as tan squared x plus 1 equals sec squared x. Since tan x equals sine x over cos x, and from the last time, sec x is the new name for 1 over cos x. So we have this very nice trig identity, closely related to the circle identity, which says tan square x plus 1 equals sec squared x. Put y equal to tan x so that x equals inverse tan of y. And dy dx is sec squared x from the previous video, which is tan squared x plus 1 from the identity we have just established. And this is just y squared plus 1. Now, we can tip over the derivative upside down using Leibniz notation, which is 1 over y squared plus 1. But x is inverse tan of y. So this says that d dy of the inverse of tan y must be 1 over y squared plus 1. Switching back to x as the typical input. So replacing y by x gives d dx of the inverse of tan x equals 1 over x squared plus 1, which is the rule for the witch of Maria Agnesi, conforming based on visualizing slopes of tangent lines. This result is one of the main ingredients in the theory of integration of rational functions, some aspects of which we will touch later on in this course. In this last part of the video, we apply the quotient rule to help us understand the second derivative of the rule for the function whose graph is the so-called witch of Maria Agnesi. The rule for this curve is y equals 1 over x squared plus 1, which turns out to be the derivative of the inverse tan function. Thank you very much for watching, and I look forward to seeing you again soon.